Hello, in this video my purpose is to show you some motivation for learning about vectors and also get you a little bit familiar with using technology to check your work. So in the first in-class activity that we had about vectors, you saw the racetrack vector game and also the hoverboard and magic carpet questions. And from that, you can definitely see how this could be related to simulating like objects moving, like video games, character movement or robot movements and whatnot. And coding all those on a computer definitely depends on vectors. Um, and with the dot and the cross product, we get to do even more things with vectors. So if you look at the other in-class activity here, there was a motivating question. And in the purpose here, I described how, the dot product is related somehow to correlation. And I asked if you could figure out what correlation is in terms of the dot and the cross product. So if you look at the website in here, you can see, okay, we have certain variables and we're trying to see if they're related somehow. And we measure that statisticians measure this by a number between -1 and 1. That's called the correlation of the data. So roughly speaking, it means that, if the data is falling closely onto a line with a positive slope, we have perfect positive correlation, and that would be 1. Meaning if one of the traits increases, the other will also increase. And a perfect negative correlation is the opposite. Correlation is -1. In that case, if one of the variables increases, the other will decrease. And those are a perfect fit. But then there's in between cases, and 0 means no correlation. The data is just scattered around. So somehow statisticians measure this, and they have formulas for figuring that out. So if you look at this example with the ice cream sales versus temperature, and there's a table in here, and also it's plotted, you can see it's pretty good positive correlation in here. And in fact, when you calculate it, is 0.9575. How do you take this bunch of dots and then spit out this number? That's the correlation. Well, at the end of this website, they tell you how to do it. And they give you an algorithm with 5 steps, which is not too hard to follow. You can do this on an Excel sheet. You have the temperature and sales columns. You subtract the mean from each to sort of make them independent of what they actually mean, just to see how far from the mean each of the quantities are. And so we have these two A and B columns, and then we multiply them to get a times b, and multiply a by itself to get a squared, and then b squared column in here. Then we sum all this up and take the sum of the a times b column and divide that by the square root of these two multiplied together, and we get the 0.9575 value. And this looks very mysterious, but somehow it's supposed to predict if two variables are correlated at all. This is very surprising. How in the world what is this formula actually measuring? How is it? Why are we doing all this computation in this way? And so statisticians, explain this by sort of trying to explain the computations, but we can think about this from the perspective of the dot product. So with that perspective, you can pause the video right now if you want to try to give this a go. If you haven't done so yet from the in-class activity, pause and try to think about it. See if you can figure out what's actually being calculated in here. Okay, so if you notice here, if you think about the A and the B as vectors, these are vectors in, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, in 12 dimensions. So they have 12 components. So when you multiply component-wise, you're getting these numbers, and when you add them up, this 5,325 number, that is just the dot product of these two vectors A and B. And then what is this 177? Well, you're squaring each component and you're adding together the components of A, and so that will be just the square of the um, magnitude of A. So by taking the square root of this number, we get actually the magnitude of A. And then the same goes about B here. We do the same computation. So what we get in here is the dot product of A and B on the numerator divided by the magnitude of A times the magnitude of B. And what is that? That should be familiar from the homework. That is the cosine of the angle between A and B. And then that cosine of the angle is equal to the correlation. So how can we think about correlation is take whatever variables you're studying, subtract the mean from each. You get these two vectors. The cosine of the angle between those two vectors in whatever dimension you're measuring, that is the correlation. And we know cosine is a number between -1 and 1. And so it makes sense why then correlation varies between -1 and 1. Without this context, without knowing that this is the cosine of an angle, it looks very mysterious. How do we know that after all this calculation, we even get the number between -1 and 1? But the mystery is solved from this perspective. So you can see here how we need here more than just 3 dimensions to think about this and solve this question. So similarly, we can think about another application. So I took this UNV vector from the learning objective 2 here, this question. Well, this one of the sample questions, there's the U and the V, and we wanted here to find the equation of the plane passing through the origin. So I typed those in GeoGebra 3D calculator. If you just Google this, it's the first thing that pops up. It's free. And you just type in U equals vector, and then you put in whatever point the vector ends at. You could also put the start and the ending point there. But we have the U and the V vector. I already put them in. And to find the equation of the plane passing through these two vectors, well, we do the cross product of the two, and that's the green vector here. It's a vector perpendicular to the two in the direction of the right-hand rule. So starting with red vector U going to blue, the right-hand rule tells us it should be in this direction. And it's exactly perpendicular to the two. Then we know that any point on the plane passing containing the vectors u and v must be connected to the vector xyz. Whatever point it's on that plane, it must have some x, y, and z coordinates. So if you take those coordinates and take the dot product with this green vector, you should get 0, because any vector, when you take the dot product of two vectors with an angle of 90 degrees, the cosine of that will be 0, and so we get a 0 as the dot product. So I know to get all the points on the plane that's perpendicular to the green vector, all I need to do is take the dot product between a general vector on that plane and this cross product. And I did that over here, and we get the equation of the plane. And we can check using GeoGebra that indeed that is the case. So this is a way to also check your work. Once you work it out on the challenge, you can quickly type it in here and see if you actually got the right answer. And once you have the equation of the plane, then we're done with that question. But I want to now reframe this whole question from a totally different perspective. Imagine we want to figure out, we want to do a Google search, okay, and we want to find something on Google. So you can think of all the web pages on Google as being the collection of all the web pages being a vector space, and it is determined by every web page is determined by certain key features, and I don't know what they could possibly be, but maybe keywords associated to that web page, some sort of ranking that is done, like some unique ID for each web page, various traits that we're interested in, and so each of those each of those web pages could be thought as being coded as a vector in some database. And then we're going to imagine that uh, the collection of all the web pages is this plane here that we got. It's two-dimensional, but of course, in reality, the database will be more than just two-dimensional. But this is what we can visualize easily. So if you imagine this being the whole database of all web pages, how does a Google search work? Where you have some sort of, you type in some keywords in the search bar, and those keywords somehow need to then be associated to web pages. How are we going to do that? Well, each of the words corresponds to some feature of those web pages. So you can imagine coding the keywords as numbers, representing some number, and so for example, this negative 2 120 here, this black vector that I have, is what I search for, is my search vector, that what I put into Google that is translated somehow into this vector, um, based on the keywords that I put in. And then now I want to figure out some web pages that are close to this. So but the web pages lie on this plane. So how do I get the web pages that are close to this black vector? Well, it means I need to really look at the projection of this vector on that plane and see what are the points close to it. So this turns into a projection question. Well, how do I find the projection now? Well, one way to do that is to, well, first project it onto the green, project this black vector onto the green vector, and I did that over here. And then once we have that projection, we'll then subtract that component, and then we should get the component in the direction of the plane, which is perpendicular to the green vector. And so that's what I did here. I took the A vector, which is our words that we're searching, and we subtract this AW vector, which is the projection of A onto the green, and we get this search vector. So this one is the closest. So then we will just have to look around this point here on this plane and see how close are other web pages. Whatever web page is the closest to this dot, that will be the first thing that shows up in your Google search, and then so on from there on. So even though this problem is totally geometric at first, and if you think about Google search, that you should feel like there's nothing that it has anything to do with geometry, but we can reframe that question from a geometric perspective and thinking about vectors as arrows in space. That helps us solve that problem that otherwise looks pretty hard to do. So this is one of the nice features of nice applications of vectors. And there's more. If you take a linear algebra course, you will learn way more applications of vectors, and computer science especially. it's full of algorithms relating to vectors. Now I wanted to